Okay, so it's my plan to record all of the lectures. Listening or watching the recording later isn't as good as being in class, obviously, because you miss all the examples that are done on the board. But this is just so you can have something to refer back to for studying if you want to go over concepts again. Hopefully that will be helpful to you, and it's easy enough for me to just clip on the microphone and record, so hopefully it works out. No guarantees that every lecture will be recorded, but that's something that I would like to do from here on out. There's a new homework assignment due a week from today, so half of it is from Chapter 4 and a little bit less than half, I guess, is from Chapter 5. So this will cover the topics that we talk about today with specific heat, and then also the beginning of Chapter 5 where we start moving into some of the open system problems and energy balance in an open system. So today we're talking about specific heat, and we're talking about it in a couple of different reference frames, both looking at specific heats for ideal gases and then also for solids and liquids, because the processes that we use will be slightly different depending on what our working fluid is. That there are certain assumptions we can make when we're working with an ideal gas that are not applicable when we're working with liquids and solids. So just as the property equations or the ideal gas equation does not apply for liquids, especially not water, you need to be very careful when you're applying some of these specific heat relations as well to make sure that your conditions are met before you start applying it to your problem. So make sure you know what the working fluid is and if it qualifies in order to make certain assumptions. So we'll talk about those assumptions in a minute, but just to give you that little bit of a warning that not all substances are created equal and how we apply the equations is not consistent across all substances, but there are certain assumptions we make which simplify it in some cases and not in others. So we're going to talk about how we can use specific heat or our knowledge of specific heat to solve these energy balances, looking at internal energy and enthalpy in order to find an alternate way to come up with those property values in our substances. So you remember before the example of touching the top of the table versus touching the leg of the table and how one of them felt different than the other. Okay, that is in part due to the fact that they have a different specific heat, meaning that it takes less energy for the table to, or it takes less energy for the leg of the table to remove heat from your hand than it does for the top of the table. So they feel different even though they are at the same temperature because they have this different quality to them. So specific heat is defined as the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree. Okay, so in other words, certain materials take more energy to heat up than others, like water versus air or steel versus plastic, that they can absorb or have energy removed from them much more readily if the specific heat is lower or higher. So different amounts of energy are required to raise the temperature of different substances. And that's a property of the substance, not necessarily a property of the process. So specific heats will allow us to compare energy storage capabilities of different materials, and it can be beneficial to us in many ways. One, if we are looking for a material that removes heat very easily, very readily from another substance by a thermal contact, then we would want something that has a very large specific heat, meaning that it can remove a lot of energy for changing that temperature. The specific heat, there's two different components to it. One is the specific heat, which is defined at constant volume, and the second is the specific heat at constant pressure. Okay, so these are two different processes that allow us to analyze or interpret whether it be internal energy or enthalpy. So if we have a process that's occurring at a constant volume, like a rigid tank, then it's going to require a certain amount of heat to raise the temperature of that tank. That will be different than if we had the same substance in a piston cylinder device. So in one of these cases, it's a constant volume process, and the other case is a constant pressure process. And if you remember from the lecture last time, as this piston cylinder moves up, we can define a boundary work term. So we have a boundary work term and an energy term on the other side of the equation, which is the M delta U. So we found that we can convert this boundary work term for a constant pressure process to P times the change in volume. And if we move that over to the other side of the equation, we have this M delta U plus P delta V. And we lumped that into a term called enthalpy. So this is review from the last lecture. If you have questions on that, you can go back to it. But in part, the definition of the specific heat depends upon whether or not this enthalpy term comes into play. So a pressure or a process at a constant volume, we use the specific heat at a constant volume, or C sub V. And the process that occurs at a constant pressure, we have a specific heat at constant pressure, which gives us delta H. Okay, so delta H is larger than delta U because we have this additional pressure term that accounts for the energy required to expand the substance. Okay, here we're constrained, we're not expanding, we're just adding heat and changing the internal energy. Here we're changing the internal energy and we are expanding the substance. Okay, the tricky bit is though, even though these are defined for a constant volume or a constant pressure process, we can apply them to any process. Okay, so if you're trying to solve for enthalpy and you want to use the specific heat and it's not necessarily a constant pressure process, you can still use the specific heat relationship. This is just how these values are determined experimentally, is via a constant pressure or a constant volume process. Okay, but the equations hold true regardless of the process. And they're properties of a substance, and they depend on the state of the substance, but they don't depend on the process. Okay, so this is what I was just saying a minute ago, that even though the specific heat at constant volume is defined for a constant volume process, that's how it was determined originally, it can still be used in applications where your volume changes. Okay, because it's a property of that substance, how that substance would behave if it were a constant volume process, but it just tells you the internal energy change based on some of the other property values. And the units, similar to the units of R, are in kilojoules per kilogram Kelvin. So it's a unit of energy per mass times temperature. And we're always looking at a delta temperature, so a change in temperature in degrees Celsius or a change in temperature in degrees Kelvin, which are equivalent. So the space between temperature units on Celsius and Kelvin scale are exactly the same. Which means we can use either degrees Celsius or Kelvin in the denominator of the equation, which is helpful to us. And then alternately, as we saw with our R values, we can replace kilojoules with a kilopascal times a meter cubed. So sometimes that's handy to know that unit conversion can occur. And then we can also write it on a unit mass basis. So if we're looking at chemical compositions and we want to know per unit per mole what is going on in the system, then we can write it on a molar basis. There was an experiment conducted by Joule, Joule, I don't remember his first name at the moment, but he wanted to determine if this change in internal energy or this specific heat of an ideal gas was a function of temperature only. So he conducted an experiment where he put two tanks into a tank of water. So one of the tanks had air at a high pressure and the other side of the tank was evacuated. So we've seen some homework problems that were similar to this. And then he opened the valve and allowed everything to reach equilibrium. So the pressures on both sides equalized, and he had a thermometer in the water the entire time to measure if there was any measurable temperature change in the water. So the previous assumption was that for something to go from a high pressure to a low pressure, there has to be a temperature change that occurs. Well, in this case, he found that actually there was no temperature change in the water because the internal energy of this system remained the same. Okay, so the air, although it's moving from one chamber and filling the evacuated side, for an ideal gas, the internal energy is only a function of temperature. So when the temperature equalized, pressure equalized, there was no change in the water temperature, which meant that there was no heat transfer that occurred, which meant that there was no change in internal energy. So this conclusion allowed him and scientists of the time to know and understand that for ideal gases they behave slightly different than a lot of other substances, as we continue to find, that they follow this ideal gas relationship where pressure and volume are a function of temperature. But even more than that, he found that internal energy was a function of temperature only. So that's a useful thing to know. Again, this only applies for ideal gases. We've already seen that internal energy is not just a function of temperature for water or for R134A, because we've used the property tables and we can look at how it changes under the dome. So even if we're operating at a constant pressure and a constant temperature, our internal energy changes from one side of the dome to another. Okay, so undergoing a phase change is not a constant internal energy process. There's a significant energy change there. But once we're so far above the critical point and we're operating in the ideal gas region, then things are only a function of temperature anymore. We don't have to worry about a phase change, and it makes things a bit more simple for us. Similarly, we can show that for an ideal gas, enthalpy, H, is also a function of temperature only. Because if enthalpy is equal to U plus PV, and we know for an ideal gas that PV is equal to RT, then H is equal to U plus RT for an ideal gas only. We already proved that internal energy was a function of temperature for an ideal gas, and R is not a function of temperature. It's a function of, it's a constant that's a property of the substance. And then, of course, temperature is a function of temperature. So H is a function of temperature also. That's big T, not little t for time. Okay, so that's very useful to us. And again, important to remember, this only applies for ideal gases. This is not for liquids or solids or other substances that are gases but aren't behaving like ideal gases, that we have to be careful about that. Okay, so because they're functions of temperature only, we can replace our partial derivatives from the previous slide with ordinary derivatives, and if we derive this equation, then U2 minus U1 is equal to the integral of CV as a function of temperature dt. Okay, so if we look at tables A17 through A25 in the appendix, there's tabulated values for ideal gas. So we have property tables for ideal gases, which I don't know if you've noticed them before or not, but we can look up the enthalpy and the internal energy just simply as a function of temperature. Okay, we don't need to worry about the pressure, we don't need to worry about specific volume. We just need to know the temperature, and then we can look it up directly from the table. Okay, so how were these tables created in the beginning? Well, there's certain relationships that we'll talk about in a minute. We'll look at some of the equations for those. Okay, so we can also determine, using this functional relationship between enthalpy and specific volume. I don't like these erasers. So if H is equal to U plus RT, as we just showed for an ideal gas, then DH will be equal to DU plus R dt. And we can substitute DH is equal to CP dt. So that's what we found here on this slide, is that this H2 minus H1, or DH, is equal to this integral of CP of T dt. Okay. So we just substitute in for DH C sub P dt and for DU C sub V dt. So then we find that there's actually a relationship between C sub P, C sub V, and R. that they're related to one another. So C sub V plus R is equal to C sub P, again, for ideal gases. And if you were to look in the tables in the back of the book and test this out yourself, you would see that C sub P plus C sub V plus R would be equal to C sub P, just from those tabulated values. So that's helpful to know too. And it also indicates, as we would expect, that C sub P is always greater than C sub V. So enthalpy is always greater than internal energy. And we can identify another property called the specific heat ratio, K, which is C sub P over C sub V. And this varies quite a bit with temperature. Well, not a lot. But for monatomic gases, this value, or this ratio between the two specific heats, is fairly constant. So this comes in handy, again, as we start normalizing substances and say, okay, I don't know specifically what is C sub P or C sub V, but I know that the ratio between the two should be about 1.667 for monatomic gas, and then 1.4 for most diatomic gases. And air is included in that, even though it's not technically a diatomic gas, but it's primarily composed of nitrogen, which is N2, and oxygen, which is O2. So it's composed of distinct diatomic gases, and so it behaves as itself, much like a diatomic gas. So we can look at these in table A2. So previously we've come to this table to look at the gas constant, but there's three other columns, C sub P, C sub V, and K. And if you were to do the math on those, you would find that C sub P is equal to C sub V plus R, and that K is equal to C sub P over C sub V. So if you want. At low pressures relative to the critical point, we discussed previously that all real gases actually do approach ideal gas behavior. And so there's something called the reduced, or the zero pressure specific heat. And there are analytical expressions that are given in A2C, so we'll look at those in just a moment. But we can look at how these gases behave if we're plotting the critical point characteristics, I guess you might say, of those ideal gases in relation to their specific heats. So this is similar, I guess, to, or analogous to, when we looked at our Z chart, and by normalizing by the critical point, we were able to see that most gases, even if they're not an ideal gas, follow certain behaviors that are consistent. This is similar. So the molar specific heats of monatomic gases are constant regardless of temperature. And then for most other gases, even if they're not constant, they're fairly linear over small temperature differences. So if we know our temperature interval and we know that it's small, there's an approximation that we can make to determine some average specific heat value. Okay, so we talked about how specific heat is a function of temperature, and table A2C actually gives that correlation, where it's C sub P in the molar form, so that line over the top indicates that the units are kilojoules per kilomole times Kelvin. And there's four individual constants, A, B, C, and D. And those vary depending on the substance that you're looking at. So nitrogen or ammonia will have a different set of constants that go into that equation, but the relationship is the same, or can be approximated as the same for all real gases. Okay, so you can take this equation then and integrate to find a functional relationship for real gases as a function of temperature in order to determine their C sub P or their C sub V. Okay, so there's this idea of constant average specific heats, which I think I need to switch the order of the slide that was just before this one and move it. Somehow it got switched. Okay, so because it's linear over a small interval, we can use an average specific heat. So we find the C sub V value at the first temperature and the C sub V value at the second temperature, and we can average those two together. Or we can just look up the C sub V or the C sub P at the average temperature. So there's two different ways to do it. One is taking the two C sub P values, C sub V or C sub P values, and averaging them together. The other is looking at the average temperature, or the temperature in the middle of those two values. And either way is about equal. You'll get approximately the same answers doing that. And this is similar to, kind of in a way, similar to interpolation, that we're looking at the two endpoints and then finding some middle ground in between, where, you know, it's the C sub p is lower here and higher here, and we're saying, okay, it's neither of those two because we're somewhere across this temperature interval during our process. We can either use that equation from the previous slide and integrate to find exactly what is our C sub p, or we can evaluate it just at an average value. And if your temperature interval is fairly small, like 100 degrees or 200 degrees, that's a pretty accurate way to do it because that slope is linear anyway. So you can look in table A2b that at various temperatures the specific heat changes. So like between 250 and 300 Kelvin, you can see it goes from 1.003 to 1.005 for air. It's not changing significantly, but there is a larger change or greater percent change for certain gases. Carbon dioxide has a larger change. And then you might find that as your temperature interval increases, or you're dealing with higher temperatures, that those changes are either greater, as they are for air, or smaller, as they are for carbon dioxide. So it kind of changes. Okay. So there's three different ways to determine delta U and delta H for an ideal gas. Okay, you might not have seen that as we went through it, but got a little bit lost in all the slides. That you can look up tabulated data, and it's easy to do. So you just go to the tables in the back of the book, table A17 through A25, and you just, if you know the temperature, you look up U, you look up H. You know the final temperature, you look up U, you look up H, and then just subtract. And that's easy. And those tables are based on somebody else who did all of the integrations and the calculations for that longer equation and tabulated it for us. Okay, so the second method, which is also accurate, very accurate, is using that equation, integrating it, and putting in the constants, which is less convenient to do, especially if you're doing it by hand. However, if you're developing a computer simulation where you would want it to automatically calculate these changes in internal energy or enthalpy, then it's very nice to have that equation. So you plug it in once, and then your computer simulation can use that equation as it changes temperature and figure out those calculations. Because the constants don't change with temperature. The constants are a constant for each substance. So nitrogen will have a certain set of constants, or carbon dioxide. But it's not really fun to do it by hand if you have to do it repeatedly. And then the third method, which is fairly accurate over small intervals and is probably completely fine for most of the problems we do in this class, is just using the average C sub p. So again, you can look it up at the average temperature from state 1 to state 2, or you can find the C sub p at state 1 and state 2 and then average those two values together. And those two methods are fairly equivalent. You won't have much discrepancy in finding the temperatures. Okay, so now that we've sort of learned about this process, let's do some examples that help to solidify the understanding of it. We have air at 300 Kelvin and 200 kilopascals, and it's heated at a constant pressure to 600 Kelvin. So we want to determine the change in internal energy of the air per unit mass using A, the data from the air table, B, the functional form of the specific heat equation, and C, the average specific heat value using that method that we just talked about. Okay, so let's first go to the table and look up air at 300 Kelvin. And we're given the pressure, but does the pressure really mean anything or matter to us? No, because this table is simply tabulated by temperature only. So table A17, in our process, we start at 300 Kelvin and we end at 600 Kelvin. So what is our change in internal energy? So what is our U at 300 Kelvin? Okay, 214.07, and what are the units on that? Okay. And what is U at 600 Kelvin? Again, kilojoules per kilogram. So part A, we can just say that delta U is equal to, and we didn't, let's see. So they want the internal energy per unit mass. They didn't give us a mass in this problem, so it's lowercase u is equal to U2 minus U1, or 434.78 minus 214.07 kilojoules per kilogram. So that value ends up being 220.71 kilojoules per kilogram. Okay, so that's part A. Part B, what do we need to do? Okay, so let's go to table A2C, right? There's a little hint there. Functional form of the specific heat equation. What is that form? Okay, if you have your books, I recommend looking at it, because it will help you learn how to do it. So C sub P, and this has a line over it. What does the line indicate? Sometimes it does. In this case, it doesn't, but this means that it's in units of kilojoules per mole, or kilomole. So we have to be careful about our units on that. Okay, so we have this functional form where it's C sub P with the line over it is equal to A plus B times temperature plus C times temperature squared plus D times temperature cubed. So what is our working fluid? Air. Okay, so we would need to look at the line for air and look up the coefficients or the constants. So A is equal to 28.11. B is equal to 0.1967 times 10 to the minus 2. C is equal to 0.4802 times 10 to the minus 5. And D is equal to negative 1.966 times 10 to the minus 9. So these are the experimentally determined coefficients for air operating in the range of 273 to 1800 Kelvin. Okay, so how do we use this? We want to find delta U, right? So du is equal to C sub V dt. We can integrate both sides of the equation, and we get delta U is equal to this integral of C sub V dt. Okay, do we have the equation for C sub V? No, we don't. We have an equation for C sub P. But what do we know about the relationship between C sub P and C sub V for an ideal gas? Yeah, they're related by that coefficient R. So C sub V is equal to C sub P minus R. And because we're dealing with the molar form, if we put our lines over the top of these, then this R turns into the universal gas constant, working in the molar form. So delta U in the molar form is going to be the integral, if we plug in this C sub P minus RU and using this equation, then we have A minus RU plus BT plus CT squared plus DT cubed dt. Okay, so then we integrate, and we get A minus RU times T plus b over 2t squared plus c over 3t cubed plus d over 4t to the fourth. Because a c sub v is c sub p minus ru, all I did was add that to the equation and combined like terms. So this a minus ru can combine here because those are the only ones that aren't multiplied by t. So it's like I'm just grouping that term here. All I've done is just move it to over by the a for convenience. I could have left it on the end of the equation and I would have an AT minus an RUT elsewhere, but since they're like terms, I just grouped them for the integration. Yeah. If I was multiplying by RU, I would have to distribute it through to everything, but just subtracting, I can put it anywhere I want in the equation. Okay, so this is evaluated from 300 Kelvin to 600 Kelvin. And if I go through and I put in all of the constants and the temperature numbers and subtract, do all that math, which I'm not going to do all on the board because it's a long process, I find that delta U with the bar over it is equal to 6,447 kilojoules per kilomole. And if I want to find in terms of kilojoules per kilogram, then I just divide through by the molar mass. So delta U without a bar over it is equal to delta U divided by capital M. So the molar mass for air is 28.97 kilograms per kilomole. So 6,447 kilojoules per kilomole divided by 28.97 kilograms per kilomole. So then the kilomoles cancel out, and that gives me kilojoules per kilogram is 222.5 kilojoules per kilogram. So pretty close to this tabulated value, right? So then the third way is using an average C sub V. So we can go again to table A2B, and we look up C sub V. We can do it two different ways. We can look up C sub V at 300 and C sub V at 600, and then average those two values. Or we can say 600 plus 300 over 2 is equal to 450 Kelvin. So that's like the average temperature of our process. And then look up C sub V at 450 Kelvin. So either of those two ways will get you approximately the same answer. So if we use this one, C sub V at 450 Kelvin is 0.733 kilojoules per kilogram Kelvin. So our delta U is just equal to C sub V average multiplied by T2 minus T1. Okay, so instead of going through the integration process, we're saying, okay, I know my C sub V varies with temperature, but I'm just going to assume that there's some average value, and it's because it's fairly linear, then that's going to be accurate enough. So if we put in the numbers for that, 0.733 kilojoules per kilogram Kelvin multiplied by 600 minus 300 Kelvin, and we get 219.9 kilojoules per kilogram. Okay, so we've completed 3 different methods to find our change in internal energy for the ideal gas given the temperatures. Okay, so in this table, A to B, there's 2 different ways to do it. We can say, okay, C sub V at 300 is, for air, is 0.718 kilojoules per kilogram Kelvin. Or C sub V at 600 is 0.764 kilojoules per kilogram Kelvin. So I can either take the average of those two numbers, and I didn't calculate that one out, so if someone wants to calculate that real quick and just tell me, and say, okay, that's my average C sub V for this process. That at 300 it's this, at 600 it's this. Since I'm changing between two different temperatures with two different C sub V's, I'm just going to say it's approximately an average. 0.741 kilojoules per kilogram Kelvin. Okay, so I can say I'll use this one, 0.741. It's the average of the two values. Or I can say I'm just going to look up C sub V at the average temperature. And then you go to the table and get the 0.733 from the table. Okay, so they're slightly different, but it's not a perfect process anyway because you're making that assumption that it's an average. So of the two, probably they're similarly different from the official or the actual answer. So you can use either way to do it. Does that answer the question? Yes?
So out of these three methods, which is the best?
Well, best is a tricky word because most accurate would be the equation. Yeah, most would be the equation with the integration. Yeah. And it is a little bit tricky because these tabulated values are supposed to be very accurate also. But you will find that there will be some discrepancies between tables in different books based on the experimental methods that they use to determine these values. Okay, so 220 versus 222, that's pretty close. It's close enough, especially when our processes aren't going to require that degree of exactness. Usually, that if it's 220 or 222, like that's close enough for whatever it is we're trying to figure out, like getting work out of a piston or something like that. So yes, this is very accurate, but again, 219 is also pretty close to 222. So why would I spend 20 minutes calculating this integral when I can spend 2 minutes using an approximation that is also very close? Okay. Now this breaks down, let's say instead of going from 300 to 600 Kelvin, I was going from like 200 Kelvin to 2400 Kelvin. Okay, that's a much larger temperature interval. So making the approximation that the specific heat is some average value over that range is not as accurate. But for 200-300 degrees, it's pretty good. And it's a lot easier to do. It saves you a lot of time. Okay, because if you want to know exactly what's going on in your system, the models break down anyway. You usually have to measure exact values. So that's that. Okay, any other questions on this?
So if it's better when you get the exact
So what was your question?
So if we're measuring the exact model, would that be an A, B, C, and D for our equation?
I'm not exactly sure how they determine A, B, C, and D. And you notice they don't give you units on those either. So it's just, I think probably they've run experiments and then they've fit like these models to their experimental data. So maybe they're measuring temperature, pressure, and volume, and they know how much heat they're adding to the system, and they're watching how the system changes with those parameters. So then they can develop this equation saying, okay, the internal energy is changing, according to this relationship between these temperature values. So I don't think they're ever measuring A, B, C, and D. I think that they're fitting a curve to some experimental data, and they say, okay, based on this curve, then our A, B, C, and D are this. If that makes sense. Okay, any other questions? Okay, let's do another problem. In this case, a student is living in a small room and turns on her 150-watt fan before she leaves for the day, hoping that her room will be cooler when she comes back in the evening. Do you think it will be? It won't be. How do we know? Because I said so. Do you believe that? You believe it? Do you believe it just because you trust me, or you believe it because you trust the energy balance? Are they one and the same? Your trust in me is because of the energy balance, or your trust in the energy balance is because of me. Okay, right, so the temperature is going to heat up. Assuming all the doors and windows are closed and disregarding any heat transfer through the walls, determine the temperature when she comes back 10 hours later. So use the specific heat values at room temperature and assume the room to be at 100 kilopascals and 15 degrees Celsius in the morning when she leaves. Which is kind of funny because if her room is 15 Celsius, that's a pretty cool temperature already. I don't know why she was trying to cool it off more. So let's do the analysis on that. How do we approach this? What information do we know? Okay, we know the volume of the room, right? So 4 meters by 6 meters by 6 meters, so 4 by 6 meters cubed. Okay, what else do we know? Okay, so the fan uses 150 watts. What type of unit is a watt? Joules per second, it's power, right? It's not energy. Okay, so W dot, meaning it's energy per time, is equal to 150 watts. How would we find energy? How would we get rid of the time factor? Yeah, you multiply it by the time interval. And what is the time interval in this case? 10 hours. Okay, so 150 joules per second. This is to find the electrical work. 150 joules per second multiplied by 10 hours. Ooh, hours and seconds don't match. What do I need to do? 3,600 seconds in an hour, not 60. Okay, so that gets rid of hours, gets rid of seconds. I'm left with joules, so we can find our electrical work is equal to 5,400 kilojoules. Is that right? Okay, so what's the next step? We want to find the temperature change. What do we do? When you're stuck, what should you do? You have to come back to it eventually. When you're stuck and you have no idea what to do, what should you do? Put your trust in the energy equation and write it down. It may help you, it may not. But when you write it down and you start canceling out terms, sometimes you realize you do know how to solve this problem. Okay, so let's just trust in the energy equation. Q in minus Q out plus work in minus work out is equal to what? Is equal to big U2 minus U1, or M times U2 minus U1. Okay, so what information do we know in this problem? Is there Q in? There's a truck driving by, I can't hear you. Q in? There's a Q in? Where's it coming from? I guess we haven't talked about how we've defined our system. So if our system is the boundaries of the room, including everything inside the room, do we have a Q in? No. If our boundary was everything except for the fan, would we have a Q in? Yes. Okay, instead of an electrical work, we would have a Q in. So we'd have to do a separate energy balance on the fan to see that the electrical work in is equal to Q out, which is the into the room. But we don't want to do that. So there's no Q in. Is there a Q out? No, we're told to disregard any heat transfer to the outside. Their work in? Yes. Their work out? No, our room's not expanding. So work in is equal to M times U2 minus U1. Okay, do we know U2 or U1? No. So how would we find those? Okay, so we can use the equation for specific heat. We could, using T1, go to the table and look up U1. But we are trying to find T2. We don't know that value, okay? So we might need to use some average specific heat in there. Okay, there's a couple different ways to solve this problem. What is U? It's equal to U sub F when we are a saturated liquid. And it's equal to U sub G when we are a saturated vapor. And then somewhere in between, you need to know the quality to find what U is. Yes. Okay, so in this case, that's not even applicable because we're a gas. So there's no liquids, there's no vapors. We're just a gas. Okay. So work in is equal to M times U2 minus U1 for an ideal gas. We can rewrite this equation as M times C sub V times T2 minus T1. Okay, because ultimately we don't really care about the internal energy change. We want T2. So then we can rearrange this equation. T2 is equal to the work in divided by this M times C sub V plus T1, or the initial temperature. Do we know the mass? No, the mass is not given to us. What's given to us? The volume. And do we know any equations that involve mass and volume and for an ideal gas? Okay, do we know the specific volume? How? Temperature. Okay, there's not a table for specific volume. But I like how you're working through this process. So we do remember that we have this equation PV is equal to mRT, right? We're given the initial pressure is just the ambient conditions. We're given the volume, or we can calculate it. We know R and we know T. So we can solve for M. So if we do that, M is equal to PV over RT. And we plug in those numbers that were given, making sure to cancel out units and to use Kelvin for the temperature. So converting 15 Celsius to Kelvin, what is that? (15 plus 273 is 288 Kelvin, right? Okay, so if we plug in all the numbers for that, we get our mass is 174.22 kilograms. And then now we can finally solve this equation. So we have our work in is equal to 5,400 kilojoules. We divide through by the mass, which is 174.22 kilograms. And C sub V, which we looked up in the table as 0.718 kilojoules per kilogram Kelvin. And then, let's see, so work in, and then plus our 15 degrees Celsius. So if we add on 15 degrees Celsius here, that means we're going to find T2 in terms of Celsius. If we add on Kelvin, if we converted the 15 to Kelvin, then we would find T2 in units of Kelvin. Okay, so this is getting messy. No. So this is like finding a delta T right here, and then you're adding it to your initial temperature. This is kilograms. Yes, mass is in kilograms. So we plug that in. So this cancels, kilojoule cancels out, kilograms cancel out. We have this K term in the bottom, which is actually a delta K or a delta degree C. So K or C is okay for this particular equation, because this is like finding a delta T. Yes, I'm going to talk about that in just a second. Okay. Yes. Because we don't know our final temperature, so we don't know how to find an average. So we're using it at 15 degrees Celsius. Okay, so plugging all those numbers in, we find T2 is equal to 58.2 degrees C, which if we add 273 to that would be what? I can't I'm standing in front of people. 331.2? 331.2 Kelvin. Okay, so you asked the question, well, we just used the C sub V at 15 degrees Celsius. If we really wanted to be thorough about this problem, we can say, okay, using that specific heat, I've solved and I found 58.2 degrees as my second value, or 331.2 Kelvin. So then you go back to the table and you find the average specific heat. Using that new specific heat, you redo the problem again until you get the final temperature would be maybe slightly different. So it can be an iterative process. In this case, the 30 degrees Kelvin difference is probably not going to be a problem. We're just saying, okay, I'm going to use a value that is close, and then if you iterate and you solve it again using an average value, knowing the final temperature, and you get approximately the same final temperature, then you're okay. But you don't have to do that on this problem. Okay, any other questions on that? Nope. Yes? You look puzzled. Your eyebrows tell me you have a question.
The room went from 15 degrees Celsius in the morning to 58 degrees.
Yeah, pretty crazy, right?
That's pretty crazy, yeah.
So, I mean, obviously there are a lot of simplifications and assumptions in this problem. It's a fairly small room. Plus, we're assuming that there's no heat transfer with the environment on the outside. So if it's 15 degrees to begin with, probably it means it's cold outside. And the fan maybe, although it's heating up the room, there's some losses to the environment. So it probably wouldn't go. But yeah, that's like 100 and something Fahrenheit, 30 something Fahrenheit.
Just out of curiosity, if there would be like a window open, would it be cooling down since it's air being sucked in?
It would depend on if the outside was cooler than the inside. Yeah, so if there was a window open and it was hot outside and you're running a fan, then your room's just going to get like even hotter. If it was colder outside, then, you know. But and that's not to say that you shouldn't ever use a fan to try to make a room feel cool. Because when you're in the room and the fan is blowing on you, it gives you the feeling of being cooler. Okay, and it's removing heat from your body quicker as wind passes over you. So the fans have a purpose. They just are not to be left on when you're not in the room. Or the example of using a window fan. So I know a lot of people will put a box fan in their window at night or something. If it's drawing in the cooler air from outside, that's different. That's a purpose. But just having the fan in the room blowing the room air around, circulating this hot air, is not going to do you any good, right? It's just going to make the air hotter. So turn your ceiling fans off and your box fans off when you leave for the day. Be energy conscious. Okay, any other questions on this problem? Let's do another one. So lots of examples to reinforce these concepts. And you'll find that even though, okay, oh man, this is now a totally different problem. It's a piston cylinder device, and I have this electrical thing, and it doesn't matter because they all are about balancing the energy in the system, using what you know to find out what you don't know. Okay, that the approach is similar or the same for most of these problems, regardless of the system, regardless of the working, not regardless of the working fluid, because we're dealing with ideal gases right now, but so it's not impossible. You can do it. Okay, so a mass of 15 kilograms of air in a piston cylinder device is heated from 25 to 77 Celsius by passing a current through a resistance heater inside the cylinder. The pressure inside the cylinder is held constant at 300 kilopascals. I like constant pressure. During the process, and a heat loss of 60 kilojoules occurs. So determine the electrical energy supplied in kilowatt hours. Okay, so what should we do? Maybe we should start with what we know about the problem. Okay, so what do we know? What? Okay, yeah. So I did a little bit of a solid for you there and wrote that stuff down, right? Okay, so the mass is known, right? Mass is 15 kilograms. And it's I know sometimes it seems redundant to go through this process, but it's important because one, maybe Professor Waite made a mistake, and you can catch my mistakes because I know you guys like doing that. But also making sure you understand the information at each state, because sometimes information is given and you're like, oh, okay, I see a temperature at 77 Celsius, you write that down. Well, that's the temperature at state 2. Maybe the temperature at state 1 is unknown. So it's important to go through and be conscious and careful as you're writing stuff down to make sure that you understand what's going on. Okay, so yes, the mass is known, T1 is known at 25 degrees Celsius, T2 is known, 77 degrees Celsius, the pressure is known, it's 300 kilopascals, and it's constant, so P1 is equal to P2. And then we're told that there's a 60 kilojoule heat loss to the surroundings. So there's some Q out equal to 60 kilojoules. Okay, so all that information was gleaned from this problem. We want to know the electrical input. Okay, so previously in problems with the resistor, we're given like the voltage and the current and the time interval, and we just calculate it. Volts times joules, or volts times amps is equal to joules. But here we're not given that. So we have to find a different way to determine the electrical. What should we do? I don't know. Oh. Let's write down the energy equation. Because if nothing else, you'll get points on an exam just for having it written down. So Q in minus Q out plus work in minus work out is equal to M times U2 minus U1. And start canceling out terms. So what do we have in this problem? Is there a Q in? Nope. What about Q out? Yes. Is there a work in? Electricity? Is there a work out? Boundary work. That's the tricky one. You have to be careful about that there is boundary work in this problem. So there will be a work out. So we have an electrical work in and a boundary work out. So good catch. Good job there, Zach. Okay, and then the mass we know. Do we know U2 and U1? No. But we know it's an ideal gas. We know initial and final temperatures. So we have ways of finding that value, right? So let's just simplify and rewrite. Get rid of all that stuff we didn't need. So negative Q out plus this electrical work in minus boundary work out is equal to M times U2 minus U1. So the boundary work for a constant pressure process, we remember from previous examples, is just the pressure times V2 minus V1 multiplied by the mass. We can move that over to the other side of the equation and combine terms so that we have M times H2 minus H1, because H is equal to U plus PV. Okay, so that's another simplification we can make, one that you just have to kind of think about and remember from previous examples. So now we have negative Q out plus electrical work in is equal to the mass times H2 minus H1. So we just combined our boundary work term into this side of the equation. Okay, so for an ideal gas, do we have any relations that allow us to solve for this H2 minus H1, or can we use tables, or what do we do? Yeah, we can just go to the property table. We know the initial and the final temperature, so why not? Okay, no more calculations are needed to look those up. So we know Q out, we know the mass, we can look up H2 and H1. So H1 is equal to 298.18 kilojoules, and H2 is 350.49 kilojoules. So if we plug all those numbers in and solve for our electrical work in, we get 844.65 kilojoules. And it's often useful to have electrical work in terms of kilowatt hours. So if we multiply by 1 hour is 3,600 seconds, and a kilowatt is a kilojoule per second, then we get 0.235 kilowatt hours. Just because that's sometimes useful. Okay, so we took the easy way out on that problem, and it's okay, because we have tables for it. We don't always have tables. Okay, real quickly, because we only have about 5 minutes, regardless of what that clock says. For solids and liquids, we can assume to a certain point that they are incompressible, or that the density is constant. Obviously, that's not the case when water is changing from a liquid to a vapor, but we're just talking about like in the compressed liquid region, we're assuming that the density is approximately constant. Okay, so C sub P and C sub V actually go to a single value because the change in internal energy is the same as the change in enthalpy for liquids and solids. So we can look at table A3 and we can find values for that. And we do a similar thing that we did for the ideal gas approximation with small temperature changes, is that we can say the change in internal energy is approximately equal to some average C value times T2 minus T1. And again, we can evaluate that average C sub V at the average temperature, or we can look up each C sub V or C, it's not a C sub V, it's a C. We can look at each temperature and then average those two values together. So it's the same kind of deal. And if we look at, from the definition of enthalpy, if our process is a constant volume process, then we have no change we have no dV term. So this just shows us that if we have H equals U plus PV, and then for solids and liquids, PV is not equal to RT, it's not a function of temperature, so we have to leave it in the equation as is. If we take a partial differential of that, then we get the VdP and the PdV terms, because pressure varies with volume and volume varies with pressure. Anyway, if our volume is not changing, we find this relationship between delta H and delta U, where it's approximately equal to just the volume now times the pressure change. Instead of pressure times delta V, it's V delta P, only for solids and liquids, and that is because it's incompressible. So if it's a constant pressure process, then our enthalpy and our internal energy will be exactly the same. And if it's a constant temperature process, then our change in enthalpy is just going to be equal to our volume times the change in pressure. Okay, so additional simplifications that can be made that are oftentimes useful. They're different than the ones we make for ideal gases, but they also make our life easier. We just have to be careful we're making the right assumptions. And we can look again in table A3. We have C values for common liquids, solids, and foods, things like that. Some of the things we'll encounter in this. And then A3B, there's additional specific heat values. Oh boy, okay, sorry, I know we're almost done. Okay, so for a constant temperature process, if we have between states 1 and 2, that H2 minus H1 is just equal to the specific volume times the pressure change. And if we assume that state 2 is a compressed liquid state and state 1 is a saturated liquid state, so for example, if we're going, if the picture is on the dome, if we're going from a saturated liquid to a compressed liquid at a constant volume, how is that going to work? Okay, like that. Then we can use this enthalpy equation, or this correction equation. We can show that it's valid for finding the enthalpy using the compressed liquid approximation or saturated liquid approximation for compressed liquids. So previously, when we've looked up U sub F, we just used the value for compressed liquids at the same temperature. We can do a similar thing for enthalpy, but in this case, we have to add in this little correction factor, because although the internal energy is not changing very much with pressure, this add-on term, this V times P minus Psat does change with pressure. So we have to have that little correction factor in there. And this is why, because of how it behaves when we increase the pressure of the substance. Okay, so that's it for today. There was one more example, but you can try to solve it on your own. I think the problems that you have in homework are not very difficult when it comes to using specific heat for solids and liquids, so you should be fine.